Hello and good morning, everyone. I'm sure you must all be happy to see me because I'm here to do your homework for you. Anyways, we'll start off with the discussion on how to mesh using unequal grid lengths. Thank you. Thank you very much. Using unequal grid lengths in OpenFOAM. You remember, until now we have been assuming that our model is divided into different grid sizes, but all of those grids are equal in length to each other. The grids in the x direction at the start till the end, all of them are equal, and the grids in the y direction also. So now we will be discussing how to change this, how to make unequal grid lengths so that we can have more number of grid points in the region where the flow is changing more rapidly. Because what happens in a fluid flow, actually, in reality, we assume the fluid flow, whenever it is happening, the molecules are flowing together. So when we are solving for it using analytical equations, we are assuming a continuum. We are assuming that there are no gaps between the points of fluid flow. There are no gaps in the region of fluid flow. But actually, when we solve it numerically, we have to provide grid points. And as soon as we provide grid points, we are assuming that the points on the grid have a discontinuity between them. They are not continuous. Then the continuum hypothesis fails. So what this leads to is that in some cases, our numerical solution is not accurate enough. And one of the reasons could be that we do not have sufficient grid points in the region of interest. Our grid may not be fine enough in the region of interest, and this leads to errors in the numerical simulation. And how to avoid those errors? The way to avoid those errors is to make a more finer mesh. But let's discuss this boundary length problem, this boundary flow. You know that the boundary layer starts developing right next to the plate and continues. However, our complete domain may be much larger. So in order to have more grid points in this region, what do we need to do? We need to create a more finer mesh over here. We need to have more grid points over here. But if we have equal grid lengths in all directions, in the y direction as well as in the x direction, that means that when we are going to have more grid points here, we are also going to have more grid points here. But we don't need more grid points here because this is free stream velocity. So in such cases, it is necessary to have more grid points in some particular region and less grid points in the other region. And that is where this unequal grid length problem comes. Moreover, what if we have more grid points throughout? What's the problem? What's the issue? The issue is computational time. As soon as we go on increasing the number of grid points, the computational time increases, the computational resources increase. And for a large problem, this can be very time consuming. A single simulation could take more than weeks to complete. So this is why meshing with unequal grid intervals is important. Next, of course, after discussing this general topic, we will come straight to our problem and discuss the flow over a flat plate. Now, this code block you will recall from our last discussion and from your homework 1. This is the line describing a block. You remember that we have to divide our domain into blocks in order to solve in OpenFOAM. In the last homework 1, you divided your model into 8 blocks. Remember, so there were 8 such hex lines. Right now we are just considering a simple case. And in this, the first is simply the ordering of the vertices. The first bracket is indicating the ordering of the vertices. The second bracket, what is it indicating? Does anyone remember what does this bracket indicate? The number of grid points in each direction, in the x direction, y direction, and z direction for this block. Okay, so this is the vertices, the vertex points, and this is the number of grid points in each x, y, and z direction. And the third one is the grading or the cell expansion ratio, which so far we had been assuming 1, 1, 1, meaning equal expansion ratios in all three directions. Now this is the change that we have, that we are assuming different expansion ratios in different directions. From here, what can we see? That 3 is the expansion ratio in the x direction, 1 is the expansion ratio in y direction, and 2 is the expansion ratio in the z direction. Now this third entry, as has been explained here, it gives the cell expansion ratio for each of the directions. And what is this ratio? How is it defined? This ratio is defined such that the width of the end cell along one edge of a block to the width of the starting cell along that edge. For example, we have a block, and we are interested in this direction, and we have many grid points. So what does this grid ratio or this expansion ratio indicate? This expansion ratio indicates the width of the end cell divided by width of the start cell, meaning the width of the end cell delta S divided by delta E divided by the width of the start cell. So this is the grading that we are going to use. So what does this tree mean? This tree means that the width of the end cell is larger and the width of the start cell is smaller. You are getting my point? Having a grid point or having a grading of 3 in the x direction means that the width of the end cell is larger and the width of the start cell is smaller. What if we want to have it opposite? What if we want to have the width of the end cell to be smaller and width of the larger cell to be the start cell to be larger? We would have to have a number less than 1. Okay, so in this case, let's consider the y direction. This is the y direction. This is the x direction. So we are interested in doing what? In increasing the mesh size in the y direction or decreasing the mesh size in the y direction. We are interested to have a finer mesh over here. So that means that we are interested in having a delta S being smaller and delta E being larger, right? A delta S at this point, the width of the start cell, and delta E, the width of the end cell. Which one do we want to be smaller? The starting one we want to be smaller, the end one we want to be larger. So what will we have in this case? We will have a positive, a greater than 1 expansion ratio, maybe 5, maybe 10, whatever we choose. And we will choose shortly. We'll just end this slide and then take a break and then come back from break, okay? So this is the simple grading. The simple grading simply specifies 3 different ratios for each of the x, y, and z direction. However, we have another type of grading called edge grading. Why do we need edge grading? Because we are talking about a block. We are talking about a block, and you remember in OpenFOAM we always have 3-dimensional blocks even for 2D problems. So a block has several edges. Okay, this is one edge, this is another edge. Let's call it A, B, C, D, and so on. Okay, so we have many edges all around the block. Using edge grading, we can specify a different grading, a different expansion ratio for each of these edges. Okay, using edge grading, we can specify a different expansion ratio for each of the edges. Let's say for edge A, I can have a different expansion ratio, but we have, let's say, F right over here at the back. Now this A is in the x direction, but F is also in the x direction. But I can have a different grading for this A and a different grading for F using edge grading technique. But of course, this is not possible using a simple grading technique. For simple grading, A, F, and this D, and let's call it G, all of these edges will have the same grading because all of them are pointing in the x direction. So this is the advantage of using edge grading. For today's lesson, we will just restrict ourselves to simple grading, but I have given an example. In this example, what is the difference between this example and this one? Basically, there is no difference because these are all the edges in the x direction. And I have chosen the grading 3 for all of the edges. So you can see the difference that over here there are only 3 grid or expansion ratios. Here we have 12 expansion ratios. So now we will take a short break, and when we come back, we will discuss an example of this in OpenFOAM. Thank you. Hello everyone. So before the break we were discussing how to create meshes with unequal grids. Now during the break I have created an example based on cavity flow, the same problem that we have already solved for homework 1 and expanded upon in homework 1. I have just created a copy of that folder, and now I will test changing the grading of our mesh length of our mesh on the example in the cavity problem. So I have copied the tutorial folder, and now I will open it just to make it larger. Yeah. Okay, remember the block mesh file, block mesh dictionary file is the file where we create the mesh and specify the grading. Now, as you see, this is right now just 1, 1, and 1. Now let's increase the mesh size in one of the directions. Let's make it 2 in the x direction, and let's make it 0.5 in the y direction. And let's observe the changes. Firstly, save this file, then go back to the OpenFOAM window, and remember the commands to run to create the mesh. Okay, generally block mesh command is used to generate the mesh, and then we can check the quality of the mesh using another command called check mesh. And if the quality of the mesh is good, at the end it will write this mesh okay. Basically it checks for various things in the quality, and for each check it writes okay. Wherever there is nothing, something which is out of the ordinary, it will display the error, and it will not write mesh OK at the end. You should understand that it may be that for your mesh, the block mesh command creates a mesh successfully, but that does not mean that your mesh has a good quality. You should check the quality of your mesh using the check mesh command, and if it says mesh OK, then your case has a higher chance of converging, meaning the solution, the numerical solution that you will run, it has a higher chance of converging. Now let's observe this in ParaFOAM. We will not run the IcoFOAM solver because right now we are only interested in checking the mesh. So do you remember how do we open our project in ParaFOAM? First we have to create a file called any .foam file in our folder. So I'll just create an empty .foam file. Let's call it mesh.foam. And now if I go back to the folder, I will see that a file has been created called mesh.foam. Now I can open ParaView and open this file in ParaView. Oops, I already had it opened. Yeah. Now I am importing the mesh, and I will just click apply, and over here we have a mesh, but we cannot yet see the meshes because it's solid. Right now I've done wireframe, and now I can see the mesh. And do you remember what expansion ratio we chose in the x direction? We chose 2 as the expansion ratio in the x direction, right? Let's show you this file. Okay, is it large enough? You can see that in the x direction we have 2. So according to our earlier discussion, expansion ratio is equal to delta E divided by delta S. So which mesh intervals should be larger? The mesh intervals further away from the origin, or mesh intervals closer to the origin? In the case of 2, in the case of expansion ratio equal to 2, expansion ratio is equal to delta E over delta S. So if the expansion ratio is 2, what does it mean? That delta E, the mesh, the width of the grid towards the end, it is twice the size of the grid at the beginning. So the grid at the beginning will be finer, the grid at the end will be coarser in the x direction. And is it the case? Yeah, it is the case that towards the end we have a coarse grid, and towards the beginning we have a finer mesh. What about in the y direction? In the y direction we have 0.5. So 0.5 is equal to delta E over delta S. Which is larger, delta E or delta S? Expansion ratio. Delta E over delta S. Okay, so if the expansion ratio is 0.5, what does it mean? Delta E is equal to 0.5 times delta S. Okay, so which is larger? Still no answer. Okay. So delta S is 2 times the 2 times delta E, meaning the first mesh width is twice the last mesh width in the y direction. And you can see that in the y direction we have a finer mesh in the upward direction and coarser mesh in the bottom. You can also view this in 2D by clicking this 3D button. Now the 3D is gone, and you can clearly view the x and y grids from this plane. If you want to change the plane, you can choose one of these. Okay, right at the top. Basically, this minus z, what does it mean? If it's saying minus z, it means that I want to look in the direction of minus z. Now z is increasing in this direction. If I am looking in this direction, I am looking in the direction of minus z. This is what these labels mean. Now moving on to the next topic. Hopefully this is clear, nothing too difficult about it, because we are simply using simple grading. If you have any questions, please feel free to ask. Otherwise, we will continue. Okay, so now we will discuss flow over a flat plate in 2D, which is our homework problem. Just have a look at the problem again. Remember the conditions outlined by professor in the last class. This is our flat plate, and we have flow entering into it from the left, or rather over it. We have flow entering over our flat plate from the left hand side. But because we are going to define our computational domain, we have to provide this y length and this x length. X length has already been provided to you by professor. If you refer to your notes from the last class, the x direction length is 10 centimeters. The y direction length has to be determined by you, because professor said you have to keep the y direction height sufficiently large so as to encompass the boundary layer. So of course, how do you do that? You first calculate the boundary layer using the analytical formula, which professor has derived and which is also included in the presentation. You calculate the boundary length using the analytical formula for your particular case. And what other specific properties does your particular case have? Your particular case has to have some u is equal to u naught. Okay, some free stream velocity, free stream inlet velocity u. So free stream inlet velocity has to be fixed by you, and the Reynolds number is also has to be chosen by you. So you have to choose the Reynolds number, the free stream velocity, and of course the kinematic viscosity nu. Of course, kinematic viscosity will determine the Reynolds number. So you either choose the Reynolds number or you choose the kinematic viscosity. And if anything I say is causing any confusion for you, please interrupt me and ask a question, and I will explain it more. So you choose the inlet velocity and the kinematic viscosity, and based on that you choose a suitable height in the y direction. Now, what are these boxes indicating? These boxes are indicating the boundary conditions which we will be using for this case. You remember, every problem has to have a boundary condition specified on all the sides of our computational domain. So our computational domain has 4 sides. But when you specify this problem in OpenFOAM, do you remember you also have to specify the third direction? You have to specify the z direction as well. But the z direction is easy. You just specify a hypothetical length in the z direction and then choose the empty boundary condition. We will see that. Okay. So the z direction is specified in OpenFOAM, but that's empty. It is basically a 2D problem. Now there are 3 boundary conditions on all 4 sides: U, V, and a boundary condition for pressure. If you refer to your notes from the last class, the left hand side will have a particular value of U and V specified. Okay, U and V will be specified on the left hand side, and of course it makes sense because the flow is entering into our domain. It must be entering at some given velocity, and we are choosing that velocity to be equal to U is equal to U naught. However, velocity is a vector. We have to specify U as well as V. We specify V equal to 0 to simplify our case. So horizontally the U velocity is entering. Let's just discuss the U velocity conditions first. The velocity conditions first, and then we will come to pressure. Now, what about the velocity conditions on the plate? The velocity conditions on the plate will be governed by the no slip condition. Okay, and therefore, due to the no slip condition, the U velocity at the plate surface will be equal to 0, as well as V velocity will be equal to 0. This also is easy to comprehend, right? Now, what is left is the top surface. Will there be any flow across the top surface? will there be any fluid going from here to the top or from the top to bottom, any flow in the Z direction? This is what we already discussed today morning. Professor was explaining to you that because when the flow enters into this computational domain, a boundary layer develops. What is a boundary layer? A boundary layer means that the velocities which are at this point are not over here. The velocities, free stream velocity u naught reduces to u is equal to 0 at this point. So what happens? The mass flow rate that is entering in the x direction, it reduces. So it has to go somewhere because for additional mass is continuously coming in, but not all of that is going out in the x direction because the plate is slowing down the velocity in the u direction. So where does the additional mass flow rate which is coming from the back, where does it go? It goes upward. So there must be some velocity interchange across this vertical direction because we specify this condition that u is equal to u naught continuously at each instance of time. So u is continuously entering our flow domain, but it cannot go forward at the same velocity because u is equal to 0 at the surface because of friction. So therefore it must go upward. It must be displaced upward. So therefore we have to have some u and v across this as well, because I have explained this point because sometimes we tend to assume that v is equal to 0 across this vertical direction. However, it is there. Nevertheless, it is very, very small. It is so small that in many numerical analyses it can be neglected because the vertical direction u is quite small. Nevertheless, to be more accurate physically, we specify this condition, which is dou v by dou y is equal to 0. Partial v by partial y is equal to 0. What does this mean? That the change in v across this surface is equal to 0. V is not equal to 0. V must be having some velocity, but if it is having a very small velocity 0.0001 just before the surface, then according to this condition, we assume that it is also having the same velocity v is equal to 0.0001 after the surface as well. So if the velocity before this surface and after this surface remains the same, what happens? The partial v by partial y is equal to 0. And this boundary condition is called the Newman boundary condition as well. And it is quite often used for these types of surfaces. Okay, hopefully the matter is clear. What does the partial v by partial y means? That it means that the rate of change of v across this boundary is 0. Now what about the end? The end surface we also don't know yet because if we because we have already specified the inlet velocity. Now we cannot fix the outlet velocity at the start. Most probably it will be some velocity which will become constant, almost constant throughout. So therefore, if the velocity across all y is almost constant, meaning at each y point the velocity before the surface and the velocity after the surface is the same, then again we can specify this Newman condition. So hopefully this is clear. Any confusion so far? The velocity conditions have all been discussed. Now we will move on to the pressure conditions. Now whenever we specify a velocity condition like u is equal to 0 or u is equal to u naught or v is equal to 0, we are constraining our problem. We are specifying a condition upon our physical problem. So if we specify a condition based on velocity, we usually tend to leave the pressure at that boundary unfixed, or the pressure at that boundary equal to Newman. So you will notice that over here when we are fixing u and v, we are leaving the pressure as having a 0 gradient. On the other hand, on this boundary, we are having both velocities as 0 gradients. So therefore now we can fix the pressure at this point. And if the pressure at this point is 0, what will happen physically if we consider our problem to be a real problem? What happens? flow, in the direction of flow, what happens to pressure? The pressure decreases in the direction of flow, right? That's why flow is taking place. Fluid flows from areas of higher pressure to areas of lower pressure. So if we are fixing the pressure over here as 0, there must be some additional pressure at the back, but because our problem is an incompressible one, this pressure is not going to have much of an effect. The value of pressure is not going to affect our problem because we are considering an incompressible problem. Anyway, so hopefully all the boundary conditions are clear, and now we can move forward. To solve this problem, I have chosen a particular set of values for all of these for the variables which are different from your homework problem, so that it does not become boring for you to do the same problem again, because you are inputting the same variables, doing the same thing again. So I am using a different set of variables. I am using a different length and other than 10 centimeters, and I've also not tested my simulation at different Reynolds numbers. So you will be left with having to test your simulation at different Reynolds numbers and having the length equal to 10 centimeters. Okay, I will show it to you in the upcoming slide. Now, the first step before we solve our actual numerical problem, we have to calculate the analytical solution, because after doing the numerical calculations, we have to compare our results, whether we are getting accurate results or not. So how do we compare? To what do we compare our results? We compare our results to the analytical solution, and the analytical solution is obtained by these equations. You remember, you have to plot two things: the boundary layer thickness and the skin friction coefficient. What is the boundary layer thickness? The boundary layer thickness is simply the y direction length of the boundary, and this is called delta, which is a function of x. Now, of course, delta is in y direction, but it is a function of x. Why? Because in the x direction it is changing. Okay, at this particular x it is very small, delta is small. At this x it is increasing. At a later x it is increasing even further. So therefore, delta is a function of x, and delta has to be plotted against x. So you are getting my point, that what you have to do is you have to plot values of delta for all x. And what are the limits of x? X starts from 0 to 10 centimeters, right? The problem, x starts from 0 to 10 centimeters. Anyways, it is too slow. Yeah, this x direction is 10 centimeters. So for each of these x, you can also generate the graph in Excel. Otherwise, you can use MATLAB or Matplotlib or plot any plotting software for your liking. It can be generated easily in Excel as well. So this is the formula you will use. Delta is equal to, then of course you have derived this formula as well. You have looked at the derivation of this formula as well. 4.92x divided by Reynolds, the local Reynolds number. Now, there is one thing very important about both of these formulas, that the local Reynolds number is being used. What is the local Reynolds number? Local Reynolds number is denoted by Rex, and the average or the total the Reynolds number over the whole length is denoted by REL. To calculate this REL, you have to substitute L in the formula for Reynolds number. U naught multiplied by L divided by nu. However, in order to use this formula, you have to substitute X in the Reynolds number formula. So remember that when you substitute this formula over here, you are changing X in the denominator and X in the numerator as well. Okay, so you have to use the local Reynolds number. This is called the local Reynolds number. This Reynolds number is changing at each instant, and this is the Reynolds number you will be using in your formula. So this is the boundary layer thickness formula, and this is the skin friction coefficient formula. Both of these will give you the value of both of these will give you a graph of delta versus x and CFX versus x. Okay, so you have two graphs now which are your analytical solution. Now you have to try to generate your numerical solution which is close to these graphs. Because if you are getting a numerical solution which is close to these graphs, then it means that your numerical solution is correct. Also notice that the conditions which change your numerical solution also change your analytical solution. You specify your length x. That length x is having an effect on your analytical solution. You specify your velocity. Okay, you specify your velocity, inlet velocity u naught. That is also having an effect on the analytical solution. You also specify the kinematic viscosity mu. That is also having an effect on your analytical solution. So whatever you specify in the numerical solution will of course logically affect your analytical solution as well. So hopefully this is also clear. Now moving forward, what type of solver will you use? We can also use UnequalFOAM for our problem. This problem, because UnequalFOAM is also an incompressible solver. However, professor has asked you to calculate skin friction coefficient, and UnequalFOAM does not allow the calculation of skin friction coefficient because it requires a turbulence model. Therefore, we are using a simpleFOAM solver. simpleFOAM is just another solver like UnequalFOAM. But so it is also a steady state solver for incompressible, but also turbulent flow. Of course, we will not be considering turbulent flow. We will specify the turbulent flow condition to be neglected and instead the laminar flow condition to be used. But because we are using simpleFOAM solver, we will be able to calculate skin friction coefficient. If you use UnequalFOAM, then you cannot calculate skin friction coefficient. Now moving on. Yeah, it is written over here. You can go through this. Now we will copy our the best way to start off with is simply to copy one of the examples. The simplest example relevant to our case is located in this folder. So I will just copy these commands. Okay, so right now I am inside the mesh example directory. I will go out of this directory in OpenFOAM. Now, yeah, this is the directory where I want to be. Now I will copy the PIDS daily, simpleFOAM PIDS daily folder to this location. You remember the commands and you remember the folders. You can also do one more thing, that when you are typing and you forget what's next, you can simply type a part of your folder name and press tab and it will complete. Okay, I have pressed I just typed IN and pressed tab on the keyboard and it will complete for me. Then I will just type simpleFOAM and press tab, it will complete. If I am typing something wrong, then it will not complete. Okay. Yeah. So now I will copy it to the current folder, but I will create a new folder inside this. Let's call this homework 02. Let's see if I have created the folder correctly. Yeah, I have this homework 02 folder. Now I'll go inside that folder. And let's see if I have the files inside, the folders inside. Yeah, I have 3 folders inside, 0, constant and system. So therefore, my problem has been, the example problem has been copied correctly. Now I'll go in the file explorer and open this. And inside it, I will open all of the relevant files. Let's just go back to the presentation and see what are the next steps. I will go through this problem solving similar to the presentation so that later on you can retrace these steps. Next, basically when we are copying the problem of PIDS daily into our folder, the PIDS daily tutorial is for something else and we are trying to modify that problem to our case. So in that folder, there are some extra files and extra conditions specified, which are not necessary for us, because you remember simpleFOAM is a turbulent solver. So it has some extra, there can be some extra conditions which can be specified to it if you are solving for a turbulent case, but we are not doing that. So what we will do, we will simply remove all the extra files and extra code that we have. What does the first step say? That in the time folder 0, remove all unnecessary initial conditions for the case. So in the time folder 0, you see there are several files, and out of these I will only leave behind P and U, because the initial conditions for our case are only the pressure and the velocity conditions. The rest of the conditions are of no use to us. They are generally most of the time used for turbulent flow. So I will delete all of them. Next, in the folder system, remove the streamlines file. This can also be done. Yeah, here, this is an extra file. Now in the turbulence properties, in the control dictionary file, remove reference to streamlines function. Now you remember we removed the streamlines file from here, this one. So now we are going to remove its reference from the control dictionary file. You can see here is a function specifying we do not need this for our case, so we will just remove it and save this file, Control S, and then move back to the presentation. Next step, turbulence properties. In the file turbulence properties, remove RAS function. RAS function is a type of solver for turbulent flow, but we do not have turbulent flow condition, so we will go in the turbulence properties file. But we do not delete this turbulence properties file. We just change it. We modify it. Okay. You can see this RAS function. We can just remove it. And in its place, what do we copy? Just look from the presentation. We copy simulation type laminar. We write simulation type laminar. Okay. And save. Now going back to the presentation. Next slide. Now we have to, customizing for the current case, turbulence properties has been changed to laminar. Now, in our case, we have to fix some suitable value of transport properties, new kinematic viscosity. Let's, of course, these are things which you will have to do through trial and error or through calculations and see what is a suitable value of nu for your case, so that you get a more accurate solution. I will just specify some random value in order to run the case and generate some results. But in order to do your homework correctly, these are the values that you will have to play with. Okay. Then change the value of nu to desired value. Then edit the following files carefully for your case. Now these are the files which specify our case. You remember block mesh dictionary is the file which will specify the vertices of our case as well as the boundary conditions for each of the faces. For your ease of use, I have written down a sample file for each of them. However, this is not reflective of your homework. You will have to change this. Why? Because as I mentioned earlier, your homework involves a plate having length 10 centimeters and I am using 40 centimeters. Okay, in this direction. Also, in the vertical direction, I am using another value. Since you are changing the x direction, you may have to change the y direction as well. So you cannot use these files as it is. You will have to change something in them, unlike the last homework. So of course, but they are very straightforward. Why? Because everything is specified. You don't have to think about too much about the code, to understand the code. You don't have to think because they are quite straightforward. Let's just discuss them. This is the block mesh dictionary file. in this, firstly we have to specify all of the vertices. I am using a single block for this case. Of course, this case can be run with a single block as well. Later on, I will tell you how more than one blocks can be used to refine your mesh further and perhaps get more accurate solutions. But it can be solved with a single block as well. So a single block will have how many vertices? 8 vertices. Those 8 vertices are specified for this block. Then because it is a single block, we generate one hex line, one hexagonal block. Now the number of meshes I have taken in the x direction to be 800. The grid length in the x direction to be 800 and in the y direction to be 300. Okay, so in this x direction we have 800 grid points, and in the y direction we have 300 grid points. And in the z direction, because the z direction is the empty boundary condition case, we are just having one grid box because our problem is a 2D problem. If it was a 3D problem, we could have specified maybe 50 or 100 meshes in the z direction as well. Simple grading. Now, what do we want? Because our boundary condition will most likely start like this. Okay. Of course, it will be much smaller, as you will notice. Generally, when we are drawing diagrams, we are enlarging our boundary condition. Our boundary length or boundary flow. It is in fact very small, as you will see in the simulation. But let's just exaggerate it and see. Our boundary condition, our boundary thickness is increasing in this direction. Okay. So what do we want? We want more mesh. If we consider the y direction, we want a finer mesh at the bottom and a coarser mesh at the top. So since we want a finer mesh at the bottom, we want a larger delta, we want a smaller delta S and a larger delta E. So that is why I am specifying for the y direction, I am specifying 5. If it's not large enough, okay. Yeah. Hopefully this is clearer. If you have any problems during the presentation, please interrupt and ask. Of course, earlier the font size was too small. Whenever I do something like that, just interrupt me. Now, so you will notice that we have 5 over here. Therefore, it means that this grid length is 5 times the first grid length. So therefore, this mesh is getting coarser in the y direction. What about the x direction? Of course, the x direction can be equal throughout as well, but I have chosen grading of 2 in the x direction, meaning more grid points, a finer mesh in this place, and a coarser mesh at the end. And of course, the z direction is meaningless for now. Any confusion so far? So this is the block mesh dictionary file which we are discussing, which is available in your presentation. You just have to modify it for your own case. Next, the block mesh dictionary file also has the boundary conditions. So this is the boundary function, the boundary list, and in this I have now divided it into 1, 2, 3, and 4 surfaces. 4 separate. Not 4. Yeah, 5. I have divided into 5 intervals. Why? Because each of these boundaries is somewhat unique. Because on each of the boundaries there is a different type of condition being applied. That is why we cannot combine any 2 of the faces. Therefore, the top boundary condition, you can see I am using a type patch with top boundary condition, and this top I will later specify how I want this to be filled. You know, if you refer to my last presentation, there are some types of boundary conditions that we use in the block mesh dictionary file, and we define the details of those boundary conditions in the U and P files. So over here we are just specifying type patch. Now what is U over here, what is P over here, we will specify in the other file. Over here we just specify type patch. This is a general boundary condition. Inlet also type patch. Outlet also type patch. But since each of these conditions has a different velocity and a different pressure, they have to be defined separately. I cannot just combine them together into one, because later on I will be specifying a different inlet condition, a different outlet condition. That is why I am putting them separately. However, all of them are simply type patch, these three. This one, and this one. The plate boundary condition is simpler because it is type wall. We have to have a no slip condition at the wall. That is why we are specifying type wall. And lastly, what is the fifth? The fifth is the front and the back faces. And also you have to specify all of these faces. You know, these you should learn how to specify these face numbers using the right hand rule. I specified them in the last presentation, described them how to list these faces using the right hand rule. Now moving on, hopefully it is clear. Any confusion in the boundary conditions so far? Now the magnitudes of these boundary conditions. The magnitudes of these boundary conditions will be specified in the U file and the P file. So this is the U file. You can see object U and dimensions. Of course, U has the dimensions of meters per second. And now you can see the usefulness of specifying the separate conditions of top, inlet, outlet, etc. So the top boundary, what is the top boundary? U is equal to U naught. So I am specifying the top boundary as equal to 0.1. And the condition, the type is being specified as free stream. Why free stream? Because of course the top boundary will be having a free stream condition most probably. Because if we have chosen our domain correctly, what will happen? The boundary layer will be somewhat at the bottom, and the top boundary condition will have free stream fluid across it with the free stream velocity. So what is the free stream boundary condition? It gives this value if there is any if there is no transfer of fluid across it, then it will give a uniform value. But if there is a transfer of fluid across it, then it will consider zero gradient. So it is a combination of zero gradient and fixed type boundary condition. In fact, many people use a fixed type boundary condition as well in this top layer, because as I told you earlier, the V velocity is so small that it can often be neglected. Even if we were to neglect the V velocity, our case would most likely be resolved correctly. But we are using the free stream boundary condition to specify that if there is any vertical flow, then take zero gradient, meaning delta V, partial V over partial Y equal to 0. But if there is no free gradient, no V velocity, then just make it equal to 0 and take 0, U is equal to 0.1. If there is any confusion, I will repeat it. I don't know why you people hesitate to ask me questions, because there is no need really. I am as much a student as you. In fact, I have learned all of this just in the last couple of days, because when I found out that I have to prepare a presentation, I learned all of them. So when I was learning, I was having many questions. So I am sure you must also be having questions, but you are not asking me. For example, I just realized I did not explain this tau n over here. Now, either you are all very intelligent and very smart and remember from the last class what the professor told you, or you did not bother to consider, or you are too shy asking me, I don't know, maybe. Do you know what is dou P over dou n? Of course, this is dou V over dou Y, partial V over partial Y. Partial V over partial Y makes sense. The change in V in the Y direction is equal to 0. But what is change in P in the N direction? The normal direction basically. Change in P in the normal direction. Normal direction to that surface. So if we are considering this surface, the change in P will be in this normal to this surface. If we are considering this surface, the change in P will be normal to this surface. So N simply represents normal to the other surface. Why? Because P is a scalar. Okay, V is a vector. So we have to specify the particular direction we are considering, but P is a scalar, and most of the time we are using N to represent the gradient of P. Now moving on, the inlet velocity condition is specified by a fixed value having x direction velocity as 0.1, y direction velocity as 0, and z direction velocity as also equal to 0. Outlet boundary condition. The outlet boundary condition is this one. Okay, and you can see over here, what do we have? The outlet boundary condition for velocity is 0 gradient. The partial u over partial x equal to 0 and partial v over partial x also equal to 0. And since this is the u file, we are only specifying the u conditions over here. The p conditions will be specified in the p file. Okay, and the plate is type no slip. Remember, we specified this as the wall. So wall will have no slip condition, and the front and back are empty. So this is the u file for our case. In fact, you can try substituting free stream with the fixed value condition and see what is the difference, if there is any change. Next, the P file. The P file is also quite straightforward. We will simply have all of these three surfaces as having 0 gradient. The bottom surface, the wall, the left surface as well as the top surface as having 0 gradient. However, the outlet will have a condition specified as uniform 0. Now you can also run this outlet with a 0 gradient and see what error does OpenFOAM show you, if there is any error. Okay, you can test all of these things. I am just giving you a simple case which will run and which will generate results, but you have to fine tune this case. Moreover, you will notice that the specification of value of P is different. It is uniform 0. However, specification of value of U is different because U is a vector. U is indicating, the capital U is indicating the velocity vector. Okay, so P is a scalar and U is a vector, and there is a difference between them. Also remember that the dimensions of pressure are those for modified pressure. They are not the physical dimensions of pressure that we have, pascals or kg per meter cube. Now, how do we run the case? We simply use our well-known commands, the block mesh, the check mesh command to check the quality of our mesh, and finally, rather than IcoFOAM, we will be using the simpleFOAM solver this time, because we have to calculate the skin friction coefficient. So now I will copy these files in my OpenFOAM folder. I will simply copy it from the earlier folder where I worked already, so that I don't have to type it all, but it is the same as I showed in the presentation. Okay, the three files, the block mesh dictionary file in the system folder and the two initial conditions file in the 0 time folder. And now let's go to OpenFOAM and see if we have done everything correctly. Okay, the block mesh has the block mesh command has run correctly. Let's now run the check mesh command. It just takes a little longer because now I am specifying a much larger number of grid length. Yeah, it is also okay. But just to show you that you have to run the check mesh command. It is always giving okay because I have already checked it. However, if you are doing this problem and you make a typo or you write something wrong, there can be a problem. And just to show you, I will make a small error and show you what type of problem we can have. Like let's say by mistake you interchanged 0.4 and 0.05. Okay. Let's save this file and then run the block mesh command. So, the block mesh command does not show any error. Okay, you see that the block mesh command has run and it does not show you any error. However, if you check for the quality of the mesh, it may show an error if it finds that this mesh is not likely to give a good solution or not likely to converge to a solution. And you can see that it has failed a mesh check, and this is not okay. So this is to show you the importance of running check mesh as well, because it may be that you get a block mesh command running successfully and you assume that you have the mesh correct mesh, but you don't. Okay, so just undo this. Yeah, save it again and then run once more. Okay, so now finally we can run our simpleFOAM command, and it will take a couple of minutes or a few minutes depending on your processor speed. In the meanwhile, we can create an empty file, the .foam file. Because we are solving for a much larger number of mesh grids, that's why it's taking a little longer. But hopefully it should be done in a couple of more minutes. In the meanwhile, I can show you the results of the case that I already have in memory, which is exactly similar to this one. Oh, it's okay. It has converged. So now we can go back to the current problem. Because it converged, so we can go back to our current case. Okay, so you remember from earlier how to import into OpenFOAM. We simply select the .form file and choose the internal mesh and click apply, and we will have the mesh generated. Now if you want to see the velocities, we can choose the velocity, u velocity vector, and select coloring of our liking. And this will create the boundary layer. Of course, for my particular case, the boundary layer is right at the bottom. And this is, but it starts from 0 and increases a little. Now your homework does not end over here. Your homework, in fact, involves creating this boundary layer profile and generating the friction coefficient, skin friction coefficient throughout. So how do you do that? Basically, in order to calculate the skin friction coefficient, you first have to realize that the skin friction coefficient is not on the internal grids. It is on the wall boundary. So when we were importing, we imported the internal mesh. In order to plot the skin friction coefficient, we have to choose the wall boundary while importing. So I will just discard this case and import once more. And while importing, I will try to ensure to select the plate from here. Okay, so I'll deselect the internal mesh and select the plate. Why? Because the skin friction coefficient values will be obtained from the plate. Moreover, before we import it, there is one more step left. The normal simpleFOAM solver does not generate the skin friction coefficient values. There is an option for the solver which we have to run before it will generate the skin friction coefficient, and then it will also not generate the skin friction coefficient directly. It will generate the wall shear stress. The wall shear stress, which is tau W, the wall shear stress. And to do this, we have to copy and paste this command. You see, simpleFOAM includes a post-processing function, which is the wall shear stress utility. And once this has been calculated, now I re-import my problem. I have to choose plate from here and then select wall shear stress only from here. And on this block, now I have to create a plot over line. Now all of this has been described in my presentation, so you don't need to worry about it, because I have highlighted all the buttons that you need to press in order to select the plot over line and how to import it. You can see I have described in this screenshot which options to select and which options to deselect. So you don't need to worry, all of it is in the presentation. But the plot over line, and on which line do we have to generate the skin friction coefficient? On the x-axis. Okay, so our line will have to be on the x-axis. So I choose x-axis from here. And these are the wall shear stress values. Of course, at the beginning of the plate, they are very large, and towards the end, they decrease. Now, how do you get them? Because you need to compare them to the analytical value. So you need to get the data points so that you can draw your graph. How do you get your data points? Firstly, ensure that you have the correct options chosen over here. Over here, this is the points X. This is the wall shear stress magnitude. And then go to File and Save Data. When you save data, you can choose a CSV file and write any name for your CSV file. Now if I go in my folder, I can see this is the wall shear stress file, and basically there are more than one column. There are more than two columns here. So which are the relevant columns? Firstly, you have to realize that there are the OpenFOAM generates values for all the axes. So you have to choose the correct axis. So you have to choose the x-axis, which is the wall shear stress on this in the first column. They are negative values. You simply multiply them by -1, and then you choose the x points. Where do you choose the x points from? You see, you have points 0, points 1, and points 2. So your points 0 is the point 0 is the column of x points, and these are the only ones which are changing. The others are constant, of course. So this is how you generate your wall shear stress. Your wall shear stress plot, and compare it with the analytical wall shear stress analytical plot. Now, of course, you have to use this formula to convert from wall shear stress to skin friction coefficient, because you have to compare to the skin friction coefficient from analytical formula. You have to use this. When you are using it, there is one more point you need to remember, that OpenFOAM uses the modified pressure dimensions, the modified pressure units. So they are meter square per second square. Since shear stress also has the same units as pressure. So the shear stress generated by OpenFOAM also has the same units of modified pressure. In order to get the actual pressure, you need to multiply it by density. But if you multiply in this formula by density in the numerator density and the denominator density will cancel out, and simply you need to specify only U0. And this makes sense because you did not specify any value of density. In order to use the value of density, you will have to generate it separately, but you don't need it. Okay, so while doing the calculation, and I have also described all of this on this slide. If you are not understanding me verbally, you can read through this later on. So this is how you generate the skin friction coefficient plot. Now, how do you find the thickness, the boundary layer thickness on your plot, on your graph, or on your figure? Basically, you have to use plot by line function again. Remember, we use plot by line. Now, we use plot by line or plot on line for skin friction coefficient on the x-axis. In order to generate the delta or the boundary layer thickness, we have to use plot by line on the y-axis. But not only on one place, but on several different places. Maybe 10 or 15 or 20, as many points as you would like. You have to have plot by line on all of these intervals, and each of those intervals will give you the same table that we saw. Now, I will do this for one value so that you don't have any confusion. I will discard this case and import it again, because now we need the U values, and U values are on the internal mesh. So now we select the internal mesh over here, and we select U and P, or only U, and deselect all others, and now click apply. And now once we have our case, we select plot by line function, and now plot by line on the y-axis. So plot by line on the y-axis, and over here you can specify, you can see that there are coordinates. This is not so clear in the it's not so clear over here, but there are coordinates. I'll just write down. These are the x coordinates, x, y, and z. Okay, so when you are using a y line, plot by line on the y-axis, the y will have a value from 0 to 0.05. I have chosen 0.05, so it will have a value of 0 to 0.05. Okay. But x will also have a value, and x will have the same value in the top and the bottom, because these are points 1 and point 2. So for x, maybe this is 5 centimeters or 4 centimeters. So it will have a value of 0.04. Okay, so 0.04 over here and 0.04 over here. So this is how you generate the first line. How do you generate the second line? You specify another value of x, 0.02, 0.02, and again draw another line here. And simply similarly for all of the different points that you would like your plot to encompass, all of those points have to be generated manually. I have searched for this. There is no easy way to do this in ParaView. In some other software like CFD-ACE or Fluent, there is a plot boundary layer thickness function, but ParaView does not have one. So you have to do this, and once you have done this, you simply click apply and save the data. This data can then be opened in Excel or in any other. And moreover, you can also save a different format data if you want to choose some other software to plot your results. And when you save it, you will have different velocities, U0, U1, and U2. Now again, remember, OpenFOAM will output all the velocities. Which ones do you want? You want the U velocity. You will choose this column. Okay. And which is the other axis? What are you doing? You are plotting the U velocity. You are trying to find out the U velocity across Y direction. So which point do you choose? You choose this column. The second column, points 1, because this is X, Y, and Z. So when you do this, you will have different U velocities. Now, for my case, I chose the U velocity to be equal to 0.1. Okay. So where is the boundary length for my case? U0. So U0 is 0.1, and 0.1 multiplied by 0.99, I will get 0.099. So that will be the point where boundary length exists. So I'll have to pass through these points until I reach 0.99, and for that point, I look at the Y value, and I copy this Y value. Okay, so this is the first point. This is the first point. The same, I have this Y value for the first point. You get the Y value and see which X is this. This is 0.2. So this is 0.2, and this is 0.004, So this is the first point. Similarly, you have to do for all of the rest of the points, and then match this curve with the analytical boundary length curve you have already from the earlier formula. Any questions or any other confusions you can ask? Otherwise, this is where we will end. In the last slide, there are some ways to improve your results. You can try running your case with different Reynolds numbers values. You can also run your case for more than one block. Right now, I have only chosen a single block and used graded meshing. But you can use 2 blocks because you saw from the other figure that the boundary layer is very thin. So maybe you can use a block in this direction and use more fine meshing in the lower block. You can also, some people have also added a block before the plate as well in the minus direction. So that can also be done, and you can experiment with these types of things to get the most accurate solution for your case. Thank you very much. Just 1 minute, I will just forgot to close this.